Welcome to the deep dive. We are jumping right into it today, and this week we are obsessing over a single word, granularity.
Granularity, yeah, that perfectly sums it up.
Because usually when we talk about AI, we are dealing with the massive stuff, trillion parameter models, global infrastructure, the big picture.
Macro level.
Exactly. But looking at the stack of research and updates from NVIDIA this past week, specifically published between February 15th and the 21st, 2026, the real story is happening in the microscopic details.
It really is. We are talking about slicing a single GPU into tiny usable fractions, or pinpointing the physical location of a memory cluster on a motherboard just to shave off a nanosecond of latency.
Yeah.
It is a very atomic wheat for AI.
It feels like we have officially moved past the phase of just building it bigger. We are now in the phase of making every single electron count.
Right.
And the hook for me this week, which I think will make a lot of you who code stop in your tracks, is about Python. For years, the rule was simple. If you want maximum speed, you write in C++ plus error. If you want ease of use, you write in Python.
That has been the golden rule of computing for decades. Python is friendly and readable, but it is slow. C++ is complex and painful, but fast.
Well, based on NVIDIA's developer blogs this week, that rule might actually be dead.
It is certainly under heavy revision.
So let's set the stage. Our mission for this deep dive is to trace how NVIDIA is transitioning from just selling hardware to defining the actual operating system of the AI world.
Yes.
We have a lot of ground to cover. We are looking at everything from sovereign AI efforts in India to the literal physics of memory latency in the data center.
It is a week where software and hardware became truly inseparable.
Let's start with segment A, focusing on research. I want to look at this concept of sovereign AI.
Let's do it.
We have a headline from the NVIDIA technical blog published on February 18th. The title is Hardware-Software Co-Designed for Sarvam AI.
Right out of India.
Yes. So what happened here is Sarvam AI is building models specifically for Indic languages, Hindi, Tamil, Telugu, and so on. But they ran into what is called the tokenization challenge.
Tokenization.
Right, which for anyone new to this is just how an AI breaks down words into numbers it can actually process.
Exactly. And why this matters so much is efficiency. Standard large language models were primarily trained on English.
Right.
So in English, one word, let's say the word computer, usually equals one token. It's highly efficient. But Indic languages have completely different script structures, complex compound characters.
So it does not translate one-to-one.
Not at all. That same single concept in Hindi might get chopped up into 5 or 6 different tokens by a standard model.
Wait, so if you are processing a sentence in Hindi, the AI has to do 5 or 6 times more mathematical work than for the exact same sentence in English.
Precisely. We call it the token tax. It made inference, the actual running of the AI, about 6 times slower and significantly more expensive for Indic languages.
That is a massive barrier if you are a nation trying to roll out AI to 1 billion people.
It is. So how did they fix it? They did not just throw bigger chips at the problem. NVIDIA and Sarvam performed extreme hardware-software co-design.
Meaning they went into the weeds.
Deep into the weeds. They rewrote the attention kernels, which is the mathematical heart of the model, and they modified the tokenizers specifically for the statistical properties of Indic scripts.
They re-engineered the core math to fit the language.
Yes, and they paired that with low-precision computing. They used FP8 and INT4 precision on the Hopper and Blackwell architectures.
What was the final metric on that?
A massive inference boost, a 4x to 6x improvement in speed and throughput. It essentially neutralized that token tax entirely.
Wow.
It serves as a blueprint for any nation wanting AI that respects their linguistic structure.
That democratizes the tech at a fundamental level. Now, shifting from language to physical movement, we also got some fascinating robotics research this week.
We did. 2 big papers.
Let's hit the first one. NVIDIA Research published a paper on February 19th called Ego Scale.
Ego Scale addresses a huge bottleneck in robotics, which is data collection.
Right, because if you want a robot to learn how to peel a banana, you usually have to simulate that exact movement thousands of times.
But Ego Scale asks a simple question. What if the robot could just watch a human do it?
But perspective matters here. It is not just watching a human from a security camera across the room.
No, it is egocentric video. First-person view.
Like wearing a head-mounted camera.
Exactly. The paper shows that robots can learn dexterous physical manipulation much faster by scaling up training on this egocentric human video data.
It bridges the gap between human physical intelligence and robotic execution.
Yes.
But then on February 20th, we get another robotics paper called VLA Perf, And this one tackles a really critical infrastructure question.
Where does the robot keep its brain?
Right, because VLA stands for Vision Language Action Models. These are heavy AI models. So do you run that on the robot's internal computer, which is physically close but maybe slow, or in the cloud, which is fast but has network lag?
This is the latency problem.
Okay.
If a robot is trying to catch a falling cup, it cannot wait 200 milliseconds for a cloud server to tell it to close its hand.
Too late. The cup is broken.
Exactly. So the VLA perf paper distills this down to 15 key takeaways on optimizing that specific latency loop.
It analyzes whether you need inference on the edge or in the server, task by task.
It is a phenomenal look at physical network constraints.
Which actually transitions us perfectly into segment B, our developer platform updates. Because if we are talking about speed and bypassing constraints, we have to talk about that Python revolution.
This was the genuine shocker of the week.
So let's look at the NVIDIA technical blog from February 18th. The headline is, Topping the GPU Mode Kernel Leaderboard with cuda.compute.
Right.
So what happened here is NVIDIA released a tool that allows high-performance kernels to be written directly in Python.
And why this matters is that developers using this specific tool actually topped the GPU mode leaderboard, beating custom C++ implementations.
For the non-programmers listening, explain the significance of that leaderboard. Is it just bragging rights?
Oh, it is much more. That leaderboard measures kernel performance. It is a test of who can write the most efficient code to make the GPU execute math. The winners are traditionally always writing in custom, highly optimized C++.
Because Python has too much overhead.
Usually, yes. But the secret sauce here is JIT, just-in-time compilation.
How does that work?
Well, C++ is typically compiled way before you ever run it. But cuda.compute takes your friendly Python code and right at the exact millisecond it needs to run, it compiles it down into highly optimized PTX machine code.
So it waits until the absolute last second.
Yes, and that is its massive advantage because if it compiles right when it runs, it knows the exact GPU it is running on and the exact shape of the data entering the system.
It optimizes for the current reality, not a hypothetical one.
Exactly. It democratizes metal-level performance. Data scientists can now write high-performance kernels without needing to master C++ syntax.
That is a massive shift for the ecosystem. Staying on the software side, on February 17th, we got a framework release for AI-ready knowledge systems.
This is the maturation of RA, Retrieval Augmented Generation.
Right. The headline from the technical blog is exactly that. Build AI-ready knowledge systems. What happened is NVIDIA provided a blueprint for enterprise retrieval.
Because for businesses, it is no longer about a chatbot that just talks naturally.
It is about a chatbot that does not lie.
Exactly. Reliable retrieval. And why this blueprint matters is the architecture it introduces, specifically judge models.
What does a judge model do?
Before your corporate data even enters the AI system, a small, specialized AI judges it. It checks for cleanliness, relevance, and formatting.
It filters the garbage out before it poisons the well.
Right. And then on the output side, they use re-ranking algorithms. So when you ask a question, the AI pulls potential answers, but then it reanalyzes and sorts those answers to ensure the absolute most relevant fact is at the top.
It turns corporate data into a verifiable audit trail.
Which is mandatory for enterprise adoption.
Absolutely. Now let's move into segment C, focusing on chips and infrastructure, because all this software ultimately runs on metal.
And the physics of that metal matter.
Let's talk about the physics of latency. On February 19th, there was a technical blog post titled NUMA Node Localization.
NUMA is an important concept here, non-uniform memory access.
You had a really good analogy for this earlier.
I think of it like a professional kitchen. You have a stove and a fridge. If your fridge is right next to your stove, you grab ingredients instantly. That is local memory.
Makes sense.
But imagine if your fridge was located in a warehouse across the street.
Dinner is going to be late.
Very late. In a modern AI server, you have multiple CPUs and multiple GPUs inside the same metal box. But the physical distance between them on the motherboard still matters.
Physics always applies.
It does. If a GPU has to pull data from memory that is physically wired to a remote CPU socket, the warehouse across the street, it suffers a latency penalty. Engineers call it delta L.
How bad is that penalty in reality?
Accessing remote memory can cause a 20 to 30% drop in throughput.
30%, just from routing across the motherboard.
Yes. In high-frequency AI, that is unacceptable.
So what did the blog post offer as a solution?
It detailed exactly how developers can pin their processing threads to the specific UNUMA node that is physically closest to the GPU slice they're using.
It forces the software to only use the fridge next to the stove.
Exactly. It is software optimization requiring extreme physical spatial awareness.
That is fascinating. Speaking of slices, we also had an update regarding stranded compute.
Ah, yes, GPU fractioning.
This was detailed on February 18th. The NVIDIA technical blog covered GPU fractioning in Run.AI.
What happened here is Run.AI updated its software to allow deep, flexible slicing of GPUs.
Because stranded compute is a huge waste of money. If a lightweight task only uses 30% of a massive Hopper GPU, the other 70% just sits there idle.
Right. And why this fractioning update matters right now is agentic AI.
Explain that connection.
Agentic AI means one single user prompt, like plan my business trip, triggers 10 independent subagents. One agent checks flights, one checks hotels, one drafts the itinerary.
And you cannot afford to spin up 10 entire GPUs for one user's trip.
No. You need to run all 10 of those small inference tasks in parallel on tiny fractions of a single GPU.
It is the economic engine that makes agentic AI viable at scale.
Precisely. Unlike traditional hardware slicing, this Run.AI update is completely software-defined.
Amazing. And orchestrating all that hardware requires some heavy lifting, which brings us to an open source release on February 18th.
The KAI Scheduler update.
Yes, version 0.12.14 on GitHub. What happened is an update to their gang scheduling algorithms.
Gang scheduling is critical for training massive models.
Right. If you need 100 GPUs to train a model, the scheduler ensures all 100 start their tasks at the exact same moment.
Because if 99 start and one is delayed, the entire cluster stalls waiting for it.
And why this specific update matters is that it now respects what they call the lowest common subtree.
Which goes right back to the physics we just talked about.
How so?
It means the scheduler actively looks for 100 GPUs that are physically network adjacent. It groups the gang closely together to minimize the cable travel time between them.
It is logistics for electrons.
Truly.
Let's pivot to Segment D, Safety, Policy, and Security. We had a critical security advisory published on February 17th by NVIDIA support.
Yes, the Megatron Bridge security update.
What happened is they patched two vulnerabilities, CVE 2025-33239 and 33240.
And why this matters is how the exploit worked. It could allow arbitrary code injection through data tutorials.
Meaning if a developer downloaded a malicious tutorial dataset to learn the system, it could silently inject bad code into their environment.
It is a stark reminder, amidst all the AI hype, basic security hygiene patching your systems immediately remains non-negotiable.
Absolutely. Security is the foundation. Now, zooming out from the data center, let's look at the edge network.
The telecom survey.
Yes. February 19th, NVIDIA Newsroom published a survey detailing AI advances in the telecommunications industry.
The numbers in this report are staggering.
They surveyed 1,000 telecom professionals globally. What happened is 89% of them reported plans to significantly increase their AI budgets.
Almost 9 out of 10.
Yes. And why this matters is the fundamental shift from basic connectivity to AI RAN radio access network.
They're turning the actual cell towers into AI sensors.
Right. So the network is not just passively broadcasting signals anymore. It uses AI to optimize spectrum usage and power distribution in real time, millisecond by millisecond.
Adapting to user load instantly.
Exactly. The survey notes that AI is now the primary driver of return on investment for telcos.
It is computing on the wire itself.
Which is a perfect segue into our final segment, Segment E, Partnerships and Enterprise Adoption, because building all this infrastructure requires massive capital.
And we got news of a massive deployment this week.
On February 17th, Reuters and the Meta Newsroom announced a major partnership.
Meta signed a multi-year, multi-generational infrastructure pact with NVIDIA.
What happened is Meta is committing heavily not just to the current chips, but to the future Blackwell and Rubin architectures.
And to understand why that matters, you have to look at the data SemiAnalysis published the day before on February 16th.
Right. SemiAnalysis ran the numbers on the new Blackwell Ultra architecture, the GB300 NVL72 rack system.
The metric they found is the key to this whole deal.
What was it?
For agentic workloads, those multi-step AI agents Meta wants to deploy to billions of users, the Blackwell Ultra system offers 50 times higher throughput per megawatt compared to the older Hopper generation.
50 times?
50, yes.
That is absurd.
But it perfectly explains the Meta deal. If Mark Zuckerberg wants to give a personal AI agent to every single user on Facebook, WhatsApp, and Instagram, They physically cannot run that on older hardware. The power grid simply could not handle it.
So the hardware efficiency dictates the actual product roadmap.
Exactly. They are locking in the future compute because the business model relies on that 50x efficiency gain.
Incredible. And finally, just to round out the adoption metrics, we had 2 quick updates showing how this standardizes across industries.
Gaming and robotics.
Right. February 19th on the NVIDIA blog, GeForce Now W officially hit 4,500 supported titles.
Which is great for gamers, but why it matters for our deep dive is that GeForce NW acts as a massive, global, distributed test bed for ultra-low latency streaming.
Right. If you can stream a high-speed video game from a data center to a cheap laptop with zero perceivable lag, you can stream inference to a robot on a factory floor.
The infrastructure is the same.
Which ties into our final release from February 17th on GitHub. Isaac ROS Cloud Control now supports the VDA 5050 standard.
This is all about fleet standardization.
What happened is they integrated this open standard, and why it matters is that now a factory manager can use the same software to control a forklift from one manufacturer and a robotic arm from a completely different manufacturer.
They finally speak the same language.
It removes the siloed ecosystems.
It does.
So synthesizing all of this, we covered a lot of ground today.
It did.
We saw Python code outperforming C++ Prey. We looked at robots learning from first-person human video. We dug into the literal physical distance between memory and processors on a motherboard, and we saw Meta buying up the future of agentic compute.
When you look at all these updates from the week together, you start to see NVIDIA building what I call a fractal architecture.
A fractal architecture. Break that down for us.
In a fractal, the core pattern repeats itself at every single scale.
Okay.
Whether NVIDIA is using run.ai to fraction a single GPU to run a tiny software agent, or they're using the KAI scheduler to orchestrate a 100,000 GPU cluster for Meta. The underlying principle is exactly the same.
Minimize the distance, optimize the latency.
Exactly. And let the software define the hardware's limits. The software layers we looked at today, cuda.compute, run.ai, they are now just as critical as the silicon itself.
It is literally an operating system for global intelligence.
That is exactly what it's becoming.
Which leaves me with one final thought for everyone listening to mull over. We spent a lot of time today talking about latency being dictated by the strict physical distance between a chip and its memory. That delta L penalty.
The physics of the motherboard.
Right. So if we are rapidly reaching the point where the actual speed of light and the physical size of a piece of silicon are our biggest bottlenecks, are we reaching the upper limits of how fast AI can physically think?
That is the big question.
Before we have to radically redesign the architecture of computers, or maybe even figure out how to redesign the laws of physics themselves,
We might have to start folding space-time in the data center.
we will definitely save that topic for a future deep dive. Thank you for joining us today, and we will see you next time.
Thanks for listening.